So we have some specific values for x sub L, x sub C, and R. Okay? And the values I'm going to use here might or might not match the values on the first question on the document. But the numbers were 4, 8, and 10 ohms. And I'm pretty sure the 10 ohms is on the resistance. And I don't even remember if the 4 was on the inductor or the capacitor, the inductive reactance or the capacitive reactance. But I'm going to treat it this way. Okay? Now I've used some colors. I've circled XL with purple. I've circled XC in orange, and I've circled R in green. And I'll continue to use those colors because what we do, we immediately, when we see this, we say, okay, my XL is going to be 4 units long, my XC is going to be 8 units long, so it's going to be twice as long as XL, and R is going to be 10 units long, so it's 2.5 times as long as XL. Well, if you want to think in terms of the biggest one, this is going to be 80% of this is going to be 40% of this. So what do? Well, my vectors are going to follow circles, so I'm going to draw the 3 circles. I'm going to draw a circle for V sub R. Incidentally, that's about as good as I get at drawing concentric circles. I'm kind of actually a little proud of that. If I was proud of such things, I really am not. So. But I'm kind of pleased to see it came up pretty well. It wasn't great. You know, that gap there's a little too much. But this reasonably represents a VR that maybe is 10. So this circle has radius 10 ohms. This circle, if this radius is 10, it's plausible this is 8. It looks more like 7 to me, but that's okay. And this one is 4. Okay. So those are going to be the maximum voltages if we assume a current, a unit current. And if we assume a bigger current, we just relabel this. The proportions are still going to be the same. Okay, well, we understand that I've drawn these pictures so that the V sub R vector can follow the green one, and the somewhat shorter V sub C vector can follow this one, and the quite a bit shorter V sub L vector can follow around this one. Then we just have to figure out where to put these, and we can put them anywhere. Ask people to draw the things anywhere but on a coordinate axis. Somebody immediately drew it on the coordinate axis, but that person knows what's going on anyway. So people drew them in different positions, and that's exactly what I wanted. Then I asked, okay, tell me what angle you want to use for V sub R. They chose 60 degrees, so that's about 60 degrees. Then I asked people, write down the angles for VL and V sub C. Well, by that time they had the knack of the idea that this was 90 degrees ahead, this is 90 degrees behind, so if this is 60 degrees, we add 60, we get 150. Now we don't need to do that in order to make a right angle here, and that's all we really have to do. We have to turn at a right angle. But it was helpful to help focus people, so you might want to think through that. What if we started at 130 degrees? What would the angles for VL and V sub C be if VR was at 130 degrees? Well, they also said VC would be at 330 degrees, which is correct. 90 degrees below this one's negative 30 degrees, and that's coterminal with 330 degrees. Although we would be better off to call it maybe negative 30 degrees to see that it's really 30 degrees behind this one. If you write it as 330, you're going to have to do a little calculation to make sure it's 90 degrees behind 60, right? Okay. So we draw the 3 vectors. There they are. Okay, and that wasn't really particularly difficult once people understood what I'd hoped they would understand coming in today. Only 2 days since the preceding class, I knew better than to hope that everybody would. And, you know, this close to finals. Okay, well, there's our picture. Now, we have to start visualizing what's going to happen now if these things start rotating at some angular frequency. Now, I said this was at 10,000 hertz. Okay? So I didn't write this up here, but this is I wrote it 10 kilohertz. That's 10,000 cycles per second. Okay, that's 20,000 pi radians per second around the circle. It takes a 10,000th of a second to make a circuit. Now we're not going to be able to see what happens, but we can detect it with an oscilloscope and so forth. And this is actually kind of what an oscilloscope would show us if we captured all three voltages. Now let's see why. As we did here, we imagine these vectors rotating maybe 30 degrees at a time. That's a good increment to use. And if we do that, if we rotate V sub r 90 degrees or 30 degrees, we're going to be here. And if we rotate it another 30, and so forth. Well, if we do that, and if we draw this thing for a series of 30-degree rotations, and I really actually recommend that you do that. If you do it one time, you'll pretty well understand it. You're going to find that the three graphs look like this. Let's just look at the VR. What's going to happen to VR? It's going to decrease. Then it's going to decrease to a minimum. Well, it decreases to 0. Here, VR is going to decrease to 0 because when we project it down onto the x-axis, this VR subvector that's here, when I draw this, is going to decrease to 0. Okay? So between, in another 30-degree increment, it's going to decrease down to 0. Okay? Then in a couple of more, it's going to decrease to where it's at its maximum negative value. So it's going to do this sort of thing. It's going to hit its negative value that's as far from 0 as possible. And then it's going to start coming back up to 0. Well, here it comes back up to 0. And then it's going to come up to a maximum here. And then it's going to come back to where it started. And then I drew it a little bit further than that to indicate that another cycle is going to start. So we just take the cycle which runs from here to here and just slap another one on here and another one. Just a repetitive cycle. Now we do the same thing for V sub c. V sub c starts here. Okay, well, let's see. The V sub r that's here, we draw that green vector and we make a mark on the axis so we know where to start our V sub r. Then we do the same with our V sub c vector and we make a mark on the axis so we know where V sub c starts. And then as we move 30 degrees, V sub c is going to increase to its maximum. And then as we go around, it's going to decrease back to 0 and then to a negative and then come back up. And V sub L, similarly, here's our V sub L vector. Well, we draw a little V sub L vector there. That's where we start. Okay? We go a little further and we have our maximum negative V sub L, which means we're down here, and then we go through our cycle. And all these are out of phase. If you draw these carefully, you'll see those phase relationships. And I'll just point them out. Here's V sub r. Here's a peak of V sub r. Now, V sub L reached its peak. Okay, now V sub r peaks here. V sub L reached its peak before this. If the thing's rotating this way, you got to rotate it back this way for V sub L. You know, what I just said is ridiculous. V sub r reaches this peak when the whole thing comes around to here. Let's look at the y-axis, okay? So that comes much later than this, but it's here. Now, by the time V sub r gets here, V sub L will have already been here. It will have reached its peak. So you see that V sub L peaks before V sub r does. And you see that by the time V sub r gets around to here so that it peaks, V sub c is 90 degrees behind it. It would be down here when V sub r is peaking, and it's got a ways to go before it peaks, so it peaks later. And the distance between, or the delay between these peaks, this to this to this, these are equal time intervals. This one is 90 degrees behind this one, which is 90 degrees behind this one. Okay, well, now we want to talk about what happens when you get the total voltage around the circuit, which is what you get when you add these voltages. We can do that from the graph. It gets a little messy. Or we can come up to our phasor diagram here and use it to get a V sub net vector that will just neatly go around the circle in some phase with the V sub r vector. In this case, the V net's back here, so it's a little bit behind the V sub r vector. So it peaks a little bit later. It'll peak right here. Well, let's take a look at that, and let's look at the graph just a little bit more.